Welcome my friends, welcome to my next lecture. Now in my last lecture I was introduced the notions of what is called contour integrations or line integral. So now I am kind of going to the week 4, though I have kind of in the I said in my earlier discussion that maybe that Cauchy-Goursat theorem I should introduce in week 3. But anyway, I think it's better to move it bring those concepts in the week 4. So this is the first lecture for week 4. So now in my last lecture I was talking about or I have introduced the notions of line integral and contour integral. Now you will see I'll first talk about that path independency. Path independency means what I'm trying to say is that if I have 2 points in the complex plane, then there could be many contour joining say point Z1 and to Z2. And then on that contour I have introduced the notions of contour integral. So now the question is, if I have a function, if I take one contour joining Z1 ending Z2, and if I take another contour joining Z1 and joining Z2, so ending Z2, so the question is what will happen the corresponding line integral or contour integral over those contours? Will the value will be same or will be different? So that's all about the path independence I will talk about, and then it will bring you one of the important theorem in complex analysis that is called Cauchy-Goursat theorem. So my plan for today's lecture is to just discuss a little bit about path independency and then the theorem what is called Cauchy-Goursat theorem. Okay, so as I said, so let me just briefly discuss briefly calculate these integrations, this contour integration. So in my last lecture I was kind of trying to calculate, but you can also do that. But let me give you very briefly the hint for how to calculate this what is called contour integrations. What is the contour? Contour is denotes the circle of radius r centered A. So now to calculate the contour integrations, first as I said, you first get the parameterizations of your contour. Now since C suffix AR denotes the circle of radius r, so what is the parameterization? Suppose CAR and suppose my parameterization is gamma. Okay, so gamma t runs from 0 to 2 pi. So what is gamma t? You can easily check. Gamma t will be, since it is a center at A and radius r, that it should be A plus r e to the power it, t runs from 0 to 2 pi. So this is my parameterizations, right? Now you just calculate. So you will have two possibilities. If n is not equal to -1, this is 0. If n is equal to -1, then it is 2 pi I. So like for example, I think if you just calculate n is not equal to -1, this case, then your integrations, contour integration CAR z minus a to the power n dz, I already discussed. If I just use the definitions of what is called contour integrations, this is 0 to 2 pi. So what is my functions? This is my functions f of z. So here my functions f of z is equal to z minus a to the power n. So by definitions it should be f of gamma t, then gamma prime t dt, right? So what is that? This is 0 to 2 pi. What is gamma t? Gamma t is a plus r e to the it. So that means it should be gamma t minus a to the power n, then gamma prime t, that means I times r times e to the it dt. But what is this? This is 0 to 2 pi. Gamma t minus a, that means this should be r to the power n e to the power I n t times I r e to the power I t dt. What is that? This is same as integration 0 to 2 pi r to the power n plus 1. Then you will have I factor will be there, and then e to the power I times n plus 1 t dt. But n plus 1 is non-zero, right? So n is not equal to -1 implies n minus 1 is non-zero. Now since this is, n plus 1 is non-zero, since this is non-zero, so I am integrating e to the power I mt on the full circle, full interval 0 to 2 pi, you just calculate it, this will give you 0. Okay, so this is the first one. So only part you have to check explicitly, n is equal to -1. Now if n is equal to -1, what will be your integrations? So then you will have integration CAR, right, 1 by z minus a dz, right? This is your functions f of z, right? So you just do that. So this is same as integration 0 to 2 pi 1 by gamma t minus a times gamma prime t. Gamma prime t means I r e to the it dt, right? And what is this? This is 0 to 2 pi, but gamma t minus a what? So this is 1 by r e to the it, then I r e to the it dt. But what is this? This will get cancelled, r will get cancelled, I will come out 0 to 2 pi dt, and what is this? This is 2 pi I, and that is this. Okay, so that means what I'm trying to say is that you can calculate contour integrations just using the definition. So main part is that if I say that calculate this contour integration, so what the first thing you need to do is that what is the corresponding parameterizations. Once you have the parameterizations, then you use the formula and you will be able to calculate what is called line integral or contour integrations. Now I come to the what is called path independency. Okay, so look, so that's what I have said. Does line integral depend on path? Depend on path means what? Suppose you have a complex plane. Suppose I have a point z1. Suppose I have a point z2, right? Then I am saying that now how many contours will be there joining z1 and ending z2? There could be infinitely many, right? So this is one, this is another c2, so this is another c3, correct? There are infinitely many contours starting at z1, ending at z2. Now each contour, suppose you have a functions, very nice functions f defined on the full complex plane to C. So in particular it is defined on each of the contours C1, C2, C3. So therefore you can have the notions of integration C1 fz dz, integration C2 fz dz, right, integration C3 fz dz. So whatever contour I can take starting at z1, ending at z2, so this kind of contour integrations you can have it. So now you can ask these questions. So now since I have starting point and ending point is fixed and I am just considering any contour joining z1, ending z2, what will be the corresponding line integral or contour integral? Will it give the same value whatever contour I can take from z1 to z2? If it happens, suppose taking 2 points z1 and z2 and whatever contour I can take starting from z1 ending at z2 and the corresponding value of the line integral or contour integral is same, then I will say that it is path independence. And if I have two different contour joining z1 and ending z2 or starting from z1 ending at z2 and the corresponding line integral values are different, then I will say that the line integral or path integral dependency. Okay, so therefore does line integral depend on the paths? So I have explicit examples. So one example I'll show you that yes, it depends on the paths. Another example I will show you that yes, it's independent of the path. But there are some kind of like behavior, like one functions you will see there are differences in the functions, like the integrand, what sort of functions I am integrating or what sort of function I am integrating with respect to some contour. Okay, let me see. First you consider this kind of functions, f of z is equal to z bar. Now this is a continuous functions, right? Now if I take some contour, since it is continuous functions and your contour, it will be like what is called line integral or contour integral will exist and it will give you some value. Okay. So now this functions f of z is equal to z bar, it is a nice function, means it is a continuous functions. Then what I am doing is that C1 is the straight line joining the point z1 is equal to 1 and z2 is equal to minus 1. Okay, you draw a picture. So this is my point 1, this is my point minus 1, right? C1 is the straight line from z1 to z2. That means I am starting from 1 and ending at 1. So that means I am moving in this direction. That is the natural orientations. And what is the corresponding parameterization? So it just you know that is the convex combination. That means gamma t is equal to 1 times, since it is starting from 1, so 1 times 1 minus t plus t times minus 1, right, or t running from 0 to 1, and that exactly I have done. So this is the corresponding parameterization. That means it is 1 minus 2t or t runs from 0 to 1. Now let me just calculate. So that means in this contour, so this is my contour C1, right? In this contour, so this is the contour integrations I would like to calculate. So integration C1 z bar dz, that means integration 0 to 1 f of gamma t, that means gamma t bar, then gamma prime t dt, that is the definitions, then 0 to 1 gamma t bar, gamma t is real 1 minus 2t, so therefore this is 1 minus 2t as it is, then gamma prime t is minus 2, and if you just calculate this integration, it will give you 0 value. So very simple Riemann integrations, it will give you 0. Now next what I will do, I will take another contour, say C2, and what is that? This is a semicircle with radius 1 centered at origin starting from 1 and ending at minus 1. So if this is the case, then you can also know the parameterizations. So it should be gamma t is equal to e to the power it, and t runs from where? Not 0 to 2 pi, but it should run from 0 to pi, because I am talking about semicircle. And there also I can easily calculate over calculate the what is called line integral or contour integral over the contour C2, right? And that exactly I have done it. Look, so I am keeping the same functions, it is a continuous functions. Now this time C2 is a semicircle centered 0 radius 1. That means this is my point 1, this is my point minus 1, and I am considering this semicircle. This is C2. And once I have the semicircle, I know the parameterizations. As I said, this is gamma t is equal to e to the it, t runs from 0 to pi. Again you can calculate this contour integrations by the formula you know. This should be 0 to pi z bar, that means gamma t bar, f of gamma t, right? Here f of z is equal to z bar. So f of gamma t means what? This should be gamma t bar, right? Gamma t bar, gamma prime t dt. Now gamma t what? Gamma t is nothing but e to the it, that means e to the power minus it, and then I times e to the it dt, and it will give you I pi. So therefore, I have a functions f of z which is z bar, and I am for taking 1 and minus 1, this is my point. So if I consider this contour C1 is a line segment starting from 1 ending at minus 1, it will give the value what? 0. But if I take another contour, say semicircle starting 1 ending at minus 1, it will give you the value I pi. But 0 is not equal to I pi. So therefore, if I take a different contour, it will give a different value of the contour integration. That means line integral or contour integral depends on the paths corresponding to this kind of functions f of z is equal to z bar. Now just the same kind of contour I will take. I have a point 1, I have a point minus 1, I have a straight line, and I have a semicircle. Okay. Now for the functions f of z is equal to z bar, it is taking two different values if I take the corresponding contour C1 and C2. Now I am changing the functions. Now I am changing, okay, so that's the conclusion. So let f of z is equal to z bar. Then the question is integrations or contour integrations over C1 is same as contour integrations over C2? Answer is no. Line integral does depends on the paths. So for example, okay, so that does depends on the paths, so just keep as it is. But you just notice that these functions, even though this function is a continuous functions, but it is nowhere analytic, right? So therefore you can guess, well, so since your function is very bad mean in a sense that I'm just having the continuity, but I do not have the analyticity, because f of z is equal to z bar, I have explained it is a very bad function, that means it is nowhere analytic. Now you can ask the questions, okay, if I replace f of the functions it is nowhere analytic like f of z is equal to z bar, now can I just say that, okay, now I want to deal with a nice function. Suppose for example f of z is equal to z. This is analytic function, right? Analytic everywhere. Now I will just take the same point 1 minus 1. One path I will have the straight line starting from 1 ending at minus 1, and another contour semicircle starting at 1 and ending at minus 1. But this time I want to calculate, or I would like to see the corresponding line integral of the functions f of z is equal to z, which is nice functions. So it is not only continuous, it is analytic everywhere. There we'll see, let's see what value should I get. It is path dependent or it is path independent. Okay, let's go ahead. Look, so for analytic functions, does line integral depends on path? That questions. Earlier on what? F of z is equal to z bar, this is nowhere analytic, means very bad functions. And we have seen that it path dependency. That means if I take one path, it will give you one value. If I take another path, it will give you another value corresponding contour integrations or line integral. Now I am changing my functions. Now this function f of z is equal to z, it is analytic everywhere. Same, I am having the point 1, having the point minus 1, C1 is the straight line, that means I have 1, I have a minus 1, now I have this curve C1, okay. Then I am, so you know the parameterization, this is 1 minus 2t, t running from 0 to 1, now you just calculate the value, this is z is z, so again same definition, 0 to 1, gamma t, gamma prime t, again you just calculate, it will give you 0. Okay, because earlier you will have z bar, now you will have z, so it will not affect because it is a real value. So this is 0, it is okay. Now let me just see the other one, C2 part. That means it is a semicircle, right? 1 minus 1, this is the one, semicircle. So you know the parameterization this. Now just calculate this corresponding line integral, integration over C2. And what is that? So integration z dz, this is again gamma t, gamma prime t. Now you see, now you will have it. You see earlier it will have z bar, that means e to the power minus it. Now it will have I times, so this is this, and gamma t is e to the it. That means I am integrating 0 to pi e to the power 2it. That means I am actually integrating e to the power it over the full interval 0 to 2 pi. And what is the value? 0. So now you see, you can have the clear differences. Now if I deal with analytic functions, so that means I am considering two paths C1, so the value will be same as integrating from C2. I mean you can expect if I take another, say lower semicircle, you check it, it is also give you 0 value. If I take another one, it will also give you 0 values. So that means the dependency of the line integral and path integral depends on the functions itself. So that means if I deal with nice functions, you can guess, yes, if I deal with say analytic functions, and if I take 2 points, so that means whatever contour I can take, well, if my function is very nice, depend on very nice domain, let it be say domain, say open connected or simply connected domain, and if I take 2 points inside my domain, and whatever contour I can take starting from one point ending from another point, so whatever contour I can take, it is expected, since I am dealing with nice function, that means analytic functions, so value should be same. That means whatever contour I can take, the corresponding contour integral will be independent of the choice of my contour. That means it will give you the same value as long as my starting point and end point will be fixed. Okay, so you can expect. So if I deal with nice function, it should be like that, and that actually give you what is called one of the nice theorem in what is complex analysis, that is called Cauchy-Goursat theorem. So I'll start with Cauchy-Goursat theorem, the statement. Of course, before that I need to say that I have to deal with nice functions along with nice domain. Okay, if I have a nice functions along with nice domain, there if I take any 2 points, and then you will see whatever contour you can take starting from one point and ending at another point, whatever contour you can take, the corresponding contour integral of course exist, and it will give you the same value. That means it is independent of the choice of the contour you can take starting from the point z1 ending at the point z2. So that means path independency will be there. Okay, so that's what. Okay, this is a conclusion. So now I have a function fz. Is this to integration sense? Answer is yes, and it is expected the line integral does not depend on the paths, because the functions you are dealing with is a analytic functions on the whole complex plane. Okay. This brings you what is called Cauchy-Goursat theorem. I will talk about more on path independency, but before that I need to have a very beautiful theorem, and there you will see path independency, and then you have indefinite integrals, everything will be there. Okay, so before that I need to just recall our domains, that means simply connected and multiply connected domain. What is the definition of simply connected domain? It says that domain means it is open connected set. Simply connected means a simply connected domain is a domain such that every simple closed contour within it encloses only points of D. That means it says that if I have a domain, if I take any simple closed contour, I can squeeze it to a point without passing through any singularities, or without passing through without going through the domain D. That's what it says. So a simply connected domain is a domain such that every simple closed contour within it encloses only points of D. That means I can squeeze my simple closed contour into a point without leaving my domain, or without passing through any singularities, something like that. So for example, if I take any simple closed contour here, okay, so I can squeeze it to a point. So same thing. So without leaving my domain, or this is the same thing, or a simple closed contour within it encloses only points of D. That means it should not happen that you can squeeze it to a point, but while squeezing, sometimes you may go out of the domain. It should not be the case. That is called simply connected domain. A domain which is not simply connected, it's called multiply connected domain. For example, this is a simply connected domain, because whatever simple closed contour I can take, the interior is only the point consisting of the point of my domain. For example, here also only the point. See, it encloses simple closed contour within it encloses only points of D, or I can squeeze it to a point without leaving the domain D. But this is the domain where it is multiply connected. Why? Because you see, if I take this simple closed contour, that is perfectly alright, because it interior only contains points of D. But now if I consider this kind of simple closed contour, now if I want to squeeze it, so if I can make it to a point, but you see at one time I will have this kind of while squeezing I will have this kind of simple closed contour where the interior there is no part of the domain, or inside bounded inside the domain bounded by this simple closed contour, this portion, white portion is living, and white portion is not a part of the domain. That means there is a hole in my domain. Those kind of domain is called multiply connected domain. So a simply connected domain is a domain such that every simple closed contour within it encloses only points of D. So that means what is the negation of that? That means if I have a simple closed contour and if it not happens, that means if there is a point which is not a part of the domain. For example, if I take this simple closed contour, this is inside inside the this portion lies inside the interior of the simple closed contour, but which is not a part of the domain. So therefore this kind of domain is called multiply connected domain, or not simply connected. In other words, you can say that a domain, if it has a hole those kind of domains is actually multiply connected domain. There are many ways you can define it, or you can say that I can take a simple closed contour, I can squeeze it to a point without leaving the domain or without passing through any singularities. So if I can do that, then it is simply connected, and if I cannot do that, then it is multiply connected. For example, you cannot squeeze it without leaving the domain, but at some point of time you have to have this kind of things, and which is actually you are away from the domain, because this portion y1 is not a part of the domain. Okay, couple of examples I have said. For example, this domain z minus z0 less than r is a simply connected, because what kind of domain it is? It is actually z0 is the center, this is z0, and it's a domain open set, center z0, and this is the one. So this is radius r, right? So z minus z0 is strictly less than r, that means it's open disk with center z0 radius r, and this is simply connected, because whatever simple closed contour I can take, interior only contains points of D, or if I take a simple closed contour, I can squeeze it to a point without leaving the domain. Okay. Interior of any simple closed contour, that is also simply connected. Okay, same thing. Suppose this is my simple closed contour, this interior, it's also simply connected domain. Again, the same properties. If I take any simple closed contour here, I can squeeze it to a point without leaving the domain, or the interior domain bounded by the simple closed contour, only the points of these are there. Okay, but the domain, this domain which is not simply connected, but what is it? Z minus Z0 is greater than R. That means if I draw a picture, this is my Z0 and this is actually the portion Z minus Z0 less than R. What is the complement? That means it says that yes, the domain is this one. Okay, this is my Z0, so this is the domain greater than R. So that means you have the whole complex plane, but there is a hole. And if there is a hole, as I said, it is not simply connected, because if I take a simple closed contour like that, this portion is not a part of the domain. I mean, it not encloses only points of D. Or I can squeeze it, this simple closed contour to a point, but at some point of time it will leave my domain. That means if I have while squeezing, if I take this kind of contour, it will, this contour and inside, it is not a part of the domain, so therefore it is leaving my domain. So therefore this is not simply connected. Similarly, if I have an annular region, that is also not simply connected. This is annular region. That means you will have this kind of domain. Suppose this is my Z0, and suppose this is what is called R1, and suppose this is R2. So what kind of domain? So if I take this, so domain is this one, less than R2. So this is, so that means it is a part of the complex plane, it is called annulus, but this portion is not a part of the domain. So this is multiply connected, because there is a hole. Because if I take a simple closed contour like this one, then the point encloses by this simple closed contour, it is this kind of points, but this is, there is a hole, it is not a part of the domain, so therefore this domain is not simply connected. Or you can say that I can squeeze it to a point, but at some point of time it will leave my domain. Okay, so therefore these are the kind of domain where you will have the domain is actually multiply connected. So now it is clear that simply connected and multiply connected. Simply connected means it is very nice, that means there is no hole, but multiply connected means it is like bad domain, there are some holes. But this is the proper mathematical definitions. For example, if I have open unit disk, this is simply connected. Okay. Once I have this domain, now you see this is one of the finest theorem, or one of the important theorem I should say. This is Cauchy-Goursat theorem on Cauchy's integral theorem. Now you see that's how it brings the difference between what is called real analysis and complex analysis. Now what is that theorem says? Look, this is famous mathematician Cauchy and this is Goursat. So that means I have a domain D which is very nice, simply connected, and I am considering a simple closed contour inside my domain, and that I am denoting at C. What is that theorem says? It says that Cauchy-Goursat theorem, actually Goursat proved Cauchy's theorem without using the hypothesis A prime is continuous. In fact, the proof I will give, I will assume that A prime is continuous. So Goursat actually proved that this theorem without assuming A prime is continuous. Okay, so that is why independently they have done it. So therefore, this is altogether I am saying this Cauchy-Goursat theorem, or sometimes it is says that Cauchy's integral theorem, or Cauchy's integral theorem for simply connected domain. So there are many books, has many names. So maybe you can say that Cauchy-Goursat theorem, or you can say that Cauchy's integral theorem, or you can say that Cauchy's integral theorem for simply connected domain. What is that? If my function f is analytic, that is very important, throughout my simply connected domain D, then it says that whatever simple closed contour I can take, this contour integrations, it takes the value 0 always for every simple closed contour C lying in D. So that is very beautiful. For example, in real analysis, can I kind of somehow say that if I deal with nice functions f and if I want to calculate integrations a to b fx dx, can I say by just in general functions f that I do not know what is my functions, and suppose only it has the nice property, say it is differentiable, right? Differentiable means it is nice. But still I cannot say anything about the value of the Riemann integrations a to b fx dx because it depending on the functions. Even if it is differentiable, infinitely many times differentiable, but unless and otherwise I do not know the expression of f, I cannot say that what is the value of the integrations a to b fx dx, right? I cannot say. Yeah, if you give me some specific function, then I can calculate it. Okay, but you see in complex analysis is very nice, right? Now I have a domain D and I have a functions which is analytic, very nice, and my domain is also nice, that means it is simply connected. Now what I am saying is that take any simple closed contour, doesn't matter, whatever simple closed contour, okay, and you know the notions of what is called contour integrations or line integration. Then it says that the line integrations of these functions f always gives you zero value. So it is a very strong theorem. So that you cannot have in the real case. Of course, real we have to interpret in a different way. But this is one of the very beautiful theorem that Cauchy-Goursat theorem says that if I start with a functions f which is analytic in my domain, and domain is nice means simply connected, then if I take any simple closed contour inside it, then the corresponding contour integrations of my functions f over the contour C, it will always have the value 0. And you later on you will see that will tell you, once I have this function and this nice domain, it will tell you that path independency. That means if I have a functions f on a simply connected domain, and if I take 2 points z1 and z2, suppose this is z1, this is z2, and whatever contour I can take, c1, c2, whatever infinitely many contours you can take starting from z1 and ending at z2, the value of the contour integrations will be independent of the choice of the contour. That means value will be same. Whatever contour I can take starting from z1 and ending at z2, and these theorems will ensure you, and that is a very beautiful theorem. Okay, so but I will prove the theorem with the assumption that my f prime is continuous. Okay, so let me just see the proof. Yeah, so of course to prove it I need to use what is called Green's theorem. So this maybe you are familiar with in your multivariable calculus course, what is Green's theorem. So I have written proof of Cauchy-Goursat theorem using Green's theorem. What is Green's theorem? So if I take a simple closed contour in R2, so if I have a R2, if I take any simple closed contour, so this is my R2, if I take any simple closed contour, let R be the region enclosed by the contour, so this is my region R, suppose this is my C. Suppose two real valued functions, say P and Q are two real valued functions, so P is a map from R2 to R, Q is a map from R2 to R, right? If I have two real valued functions, together I demand something, what is that? Together with that first order partial derivatives exist and continuous inside the contour, that means inside R, inside or on R. So okay, so therefore I have a contour, let the interior or let the domain bounded by C, it is R. Take two real valued functions P and Q, which is nice, that means suppose first order partial derivative exists and they are continuous, then this is the corresponding Green's theorem. Somehow it says that integrations over C, that means over the contour, it's same as integration over the region R. So somehow we can say that so double integral reduces to a single integral, or like integral over R2, it boils down to integrals over R, something like that you can think. So you can interpret also as a what is called fundamental theorem in more than one dimension. That means in the right hand side I have integrations over R, that means in a region in R2, that means in R this is a region, and then it gives a connections with the integrations over on the boundary. Now this is 2 dimension, right? Now if I have the integrations over C, this is 1 dimension. So somehow it is reducing the dimension, right? So integrations over 2 dimensional object, that means on R, it reduces to the integrations over 1 dimension, that means over the contour. So in that way you can think about it is fundamental theorem, because fundamental theorem, what is that? Integrations a to b, f prime t dt, which is exactly fb minus fa, right? That means integrations over the interval a to b, that means 1 dimension, reduces to the value of the functions at 2 endpoints. So that means somehow 1 dimension reduces to 0 dimension, you can think about. They are also actually 2 dimension reduces to 1 dimension. So you can think, you can interpret in this way. But this is the statement of Green's theorem. So if I have a simple closed contour in R2, and if I say that R is the region enclosed by my contour C, and if I have two nice functions P and Q from R to R, then the integrations over C is exactly equal to integrations over R, but this time of course integrand will change. So integration C P dx plus Q dy is equal to double integration over R Qx minus Py. Qx Py means it is del Q del x, and this is del P del y. Partial derivative of P with respect to y and partial derivative of Q with respect to x with respect to the area measure on R. Okay. I need to use this theorem to prove what is called Cauchy-Goursat theorem. Okay, let me just see the proof. So that means what? That means I have this assumption, I have a domain, I have a simple closed contour, and I have to say conclude that this contour integration is 0. And contour integration formula you know, somehow I have to use the formula along with Green's theorem, it will tell you. Okay, so this is the one. So since f it's a complex valued functions of complex variable, so f will have the form u plus iv. Now look, f is analytic is given on a simply connected domain, so one can easily check that it follows that the first order partial derivatives of ux, uy, vx, vy are all exist and they are continuous. I already discussed if my function is analytic, then u and v both first order partial derivative will exist, they are continuous. Okay, so that part is okay. Furthermore, of course, since analyticity is there, it should satisfy Cauchy-Riemann equation, that means ux is equal to vy and uy is equal to minus vx. So therefore the assumption that my function is analytic will automatically implies that all the first order partial derivative of u exist, they are continuous and they satisfy Cauchy-Riemann equations. And also if I have the f prime, what is the f prime? This is ux plus I vx, and ux and vx are continuous, so therefore f prime is continuous. So analyticity of f implies f prime is continuous. In fact, later on you will see if my function is analytic, then f prime is also analytic. In fact, f double prime, any derivative of f, that is also analytic. So that means later on you will see, but only analyticity of f for the time being, whatever we need it, just f prime, and the fact that ux, uy, vx, vy all exist and continuous, so therefore f prime is continuous. So therefore analyticity implies that all the first order partial derivative of u exist, they are continuous, in particular f prime is continuous. Okay. Now once I have this one, then I will use what is called Green's theorem. Look, so this is my functions, f is equal to u plus ib. Now you have a simple closed contour, right? You have a simple closed contour, right? So suppose it will have a parameterization. Of course, as I said, you need a parameterization, then you can use the definitions of contour integrations, right? So suppose this is my parameterizations gamma t, which is xt plus I yt. Suppose t runs from a to b, it's a parameterizations. Then what is this integration c fz dz? That is by definitions the contour integrations a to b f of gamma t, gamma prime t dt, right? That's by definition I said. Now f of gamma t, you have expression of f u plus ib, so therefore you have u is equal to xt yt plus I times v of xt comma yt, like because gamma t is xt comma yt, right? You can think about gamma t xt comma yt, right? And f is equal to u comma v, right? So therefore this is proportions f of gamma t. And what is gamma prime t? This is again x prime t comma y prime t, right? Because gamma is this one, so xt comma yt, so what is the derivative, corresponding component derivative, right? So you just do the algebra. If I do the algebra, then it turns out that it should be u x prime minus b y prime dt plus I times b x prime plus u y prime dt. And what is x prime? X prime is actually derivative of x, that's what it is. So that means x prime of t means d x prime of t, that means you can say that this is dx dt, that's what I am trying to say. Okay. So if from the, do some algebra, you will have this one. Now what is that? Look, so then I can say that this is same as I can replace, or I can write this object integrations a to b u x prime minus b y prime dt by contour integrations over R2, because if I take a contour C, so this is boils down to integration C u dx minus v dy by the definitions of the contour integrations in R2 or line integral in R2. If you just recall, you can write this object u x prime minus b y prime dt to integration c u dx minus b dy, and this portion you can write by definitions of the contour integrations in R2 integration c v dx plus u dy, right? So that is, now I am in like integrations over line integrations over the contour in R2. Now you have to use what is called Green's theorem. Now integrations over the contour, I can replace to the integrations over R, that means 2-dimensional integrations, but of course the integrand will change because of this formula. So if I have p dx plus q dy, then it will be qx minus py. If I do that one, so then this is integrations over R minus vx, because v minus vx minus uy dx dy, then what will happen, p dx plus q dy, right, p dx plus q dy, so this will be qx minus py, so of course this is minus vx minus uy dx dy, then this is ux minus vy dx dy, that is perfectly alright. So therefore from here to here I have applied what is called Green's theorem to change my integrations over contour to the integrations over R. Okay, that is using what is called Green's theorem, and that is actually by definitions of the contour integrations or line integration in R2. Okay, so if I have a parameterizations, so u x prime t dt, that means u dx. So that means what I am trying to say is that integration c u dx by definition it is nothing but a to b u x prime t dt. That's what it says. Okay, so that is the definitions. Now this is by Green's theorem I am done. Now I have more on that because my function is analytic, so that my ux, ui, vx, vy satisfies CR equations. If I use CR equations, see ux is equal to vy, that means it will give you the integrand is 0, ux is equal to vi, this is 0, and ui is equal to minus vx, that is also 0. So that is 0, that is 0 because of CR equations or because of analyticity of it. So therefore at the end of the day I will have the integration is, see integrand is 0, so therefore integration value is 0. So this is by using CR equations. So this is the proof of my Cauchy-Goursat theorem. So it is very straightforward proof. That means you have to just use Green's theorem, okay, in R2 that you are probably familiar with in multivariable calculus. So if you know Green's theorem, then you can easily prove Cauchy-Goursat theorem for simply connected domain just by using the definitions of contour integrations. Just write your contour in a parametric form, you write f is equal to u plus iv, use the definition of contour integrations, then you use Green's theorem to change the contour integrations or integrations over the contour to integrations over a region, then use what is called analyticity of f, that means ux, uy and vx, vy satisfies or uv satisfies Cauchy-Riemann equations, it will give you that the corresponding contour integration is 0. And whatever contour, any contour, whatever simple closed contour I am taking, the corresponding value of the contour integration is 0. Okay, so I have given a reference for a proof without using Green's theorem. This is very kind of easy if I use Green's theorem, but if you would like to see without using Green's theorem can I prove Cauchy-Goursat theorem, answer is yes. So then you just deal with complex analysis by Alfors. That book if you see, there he proved Cauchy-Goursat theorem without using Green's theorem. Okay. Okay, so that's the proof. Now I have just applications of Cauchy's theorem or Cauchy-Goursat theorem. Now you see, once I have this theorem and then if I say that okay calculate these contour integrations, then you don't have to calculate it. If you somehow kind of observe that yes it satisfies all the hypotheses of my Cauchy-Goursat theorem, then without calculating the contour integration you can say that value is 0. For example, if I take this my parameterization, this is my circle. What is my parameter? So C is a circle of radius 1. So that means this is my circle. If I have a circle, this is the parameterization, you can have it. Gamma of t is equal to e to the power it, t runs from minus pi to pi. Then you see, if I consider the functions, it follows that by Cauchy's theorem, integration c f z dz is 0. Now look, what are my functions? See, I have functions f of z is equal to e to the power zn cosine z sin z. Now then you can easily say that f of z, if I take a sin z, it is analytic functions everywhere in the complex plane. And in complex plane it is a simply connected domain. Now this unit circle is a simple closed contour sitting inside. So therefore by Cauchy-Goursat theorem this integral is 0. That's it. You don't have to calculate. You don't, even if the parameterization is given, you don't have to say that okay this is same as minus pi to pi f of gamma t gamma prime t dt, right? You don't have to calculate. Well, for this kind of functions, if you calculate, you cannot do that. It will be very difficult to calculate this kind of integrations. Rather, you just use the theorem. So that is the beauty or applications of Cauchy-Goursat theorem. You don't have to calculate using the formula of contour integrations. By looking at the functions, by looking at the domain, and if your domain is simply connected, your function is analytic, and if you somehow say that yes, the simple closed contour sitting inside my domain, then without calculating you can say that by Cauchy-Goursat theorem this integration is 0. Okay, so this is 0 because all functions are analytic everywhere in the complex plane, and unit circle is a simply connected contour inside this domain. So therefore by Cauchy-Goursat theorem, these contour integrations always gives me 0. You don't have to calculate using the formula of the contour integrations. Even you cannot do that for this kind of functions. Even if you use the what is called contour integrations formula, like if you have the parameterizations, you have the functions explicitly. If you write from a to b f of gamma t gamma prime t dt, it will be very difficult to calculate. So you can just instead you just use what is called Cauchy-Goursat theorem. You can conclude it. This is another one. So look at this functions. This is f of z. What is my functions? F of z e to the power I z square divided by z square plus 4, right? This is my functions. Okay, what is my contour C? Unit circle. So I have a, say, unit circle is there. Now look, what kind of function is this? These functions you can easily guess at z is equal to plus minus 2, there will be a problem. That means my functions lose the analyticity. So therefore this function is not, even though this function is numerator is analytic, but denominator will have like singularities at the point plus minus 2, right? So therefore this function is not analytic on the whole complex planes. Okay, perfectly all right. So what I will do, I have a unit circle, so this is 1. What I will do, I will consider a circle of radius say 2. Okay, so I am considering a circle or domain say center 0, radius 2. Okay. So this is my domain. What is this? This is a ball or disk of center 0, radius 2. Okay. So this is my domain. Now in that domain, open. So that means I can say that this is the domain, although z is equal to c, such that modulus of z is strictly less than 2. So this is a disk of center 0, radius 2, right? Open unit disk. That means I am not considering the boundary, which is strictly less than. So this is, in this domain, this function is perfectly all right. This function is analytic functions because it will have a singularity plus minus 2, but I am considering the open unit disk. That means I am not considering the boundary part. That means here the point plus minus 2 is not there. So therefore there my function is analytic. And what kind of domain? If you remember, open unit disk with some center and some radius, it is always simply connected domain. So therefore this domain is simply connected. This is simply connected. This domain, my function is analytic, and the unit circle of radius 1 which is sitting inside, it is a simple closed contour. So therefore what is my Cauchy-Goursat theorem says? Integrations over C of this f should be 0. So that's exactly I have written. So this integration is 0 by Cauchy's theorem. Note that the integrand is not analytic at the point z is equal to plus minus 2, but that does not bother us because these points are not enclosed by my contour C. Because even though it has a singularity at plus minus 2, but the contour integrations I am talking about over the contour, the domain or the domain part, the domain enclosed by C, the plus minus 2 is not there. In other words, I am considering the domain of or a disk which is centered 0 and radius 2. In that domain which is simply connected, unit circle is a simple closed contour which is sitting inside. My function, it is analytic in that domain. So therefore by Cauchy-Goursat theorem this is 0. Okay, so that's how you can use Cauchy-Goursat theorem to conclude many contour integrations without evaluating it by using the formula, by using the parameterization. So that's what I have written. That does not bother us as these points are not enclosed by C. That means even though plus minus 2 is a singularity, but the domain I am considering and the contour I am considering inside the domain, in that domain my function is nice, and I have a simple closed contour sitting inside. So therefore by Cauchy-Goursat theorem integration is 0. So in that way you can calculate many contour integrations. Okay, so first you see what is your functions, what is your domain. And if you see your domain is nice, that is simply connected, and your contour simply contour C sitting inside, then simple closed contour sitting inside your domain, then you can just use Cauchy-Goursat theorem, say that this integration, contour integration is just value of the contour integration is 0 without like calculating your contour integration explicitly. Okay, so now that's all from this lecture. So once I have this Cauchy-Goursat theorem, in my next lecture you will see it will help you to talk about the existence of primitive. Right, to talk about the existence of primitive or to talk about the independency of path. That means if my domain is nice, function is nice, if I take any 2 points inside the domain, whatever contour I can take starting one point and ending at point, value of the contour integration will be same. That means path independency will be there. But there you need like nice assumption. That means my domain should be nice and my function should be analytic. Then everything will be perfectly all right, all kind of stuff. I think I should stop here. In my next lecture, I will talk about path independency, then existence of primitive, so on and so forth. Thank you.